In this video, we will give a brief overview of rule sets and reasoning strategies. Let's get started. A rule set consists of prefixes, or namespace prefixes, axiomatic triples, and custom rules. Predefined rule sets are empty, no reasoning. GraphDB operates as a plain RDF store. RDFS, standard RDFS semantics. OWLHorst, RDFS plus D entailment plus some OWL minus tractable. OWLMax, RDFS with most of OWLLite. OWL2RL, conformant OWL2RL profile except for D entailment. OWL2QL, reasoning over large volumes of data. The two reasoning strategies are forward chaining and backward chaining. With forward chaining, inferences are pre-computed. You have faster query performance, but have slower load times and use more memory or disk space. With regard to backward chaining, inferences are performed as needed at query time. You have slower query performance, but faster load times. In some cases, there is also a hybrid reasoning. This includes a partial forward chaining at data loading time, plus partial backward chaining at query time. If you want to use GraphDB for reasoning optimizations, you need to know that most triple stores perform an expensive full recompute on updates. The first optimization tactic is reasoning on insert. This is a forward chaining optimization, where rule sets compile to fast Java code. Every statement is passed through all rules. The first check is in memory, reducing the need for lookups. The second optimization tactic is delete optimization, or smooth incremental delete. In this case, truth maintenance minimizes the recompute, but the required dependency tracking is expensive. GraphDB optimizes deletes by using backward chaining to derive delete dependencies dynamically. This backward search stops at axioms or ontology triples. You need to check onto schema transaction to control it. The inferred triples without alternative support are retracted. To make an OWL same as optimization, you need to consider the following. Same as is useful in semantic data integration. Often independent agencies mint different URLs for the same entity. Same as, in equivalence relation, declares them the same smushing. All statements of URL X in equivalence cluster are copied to all Y in the same cluster. Such inference causes a combinatorial explosion of statements. If unchecked, this decreases memory and query time performance. Same as optimization includes compact representation. Statements are made against clusters, not against individual URLs. Backward chaining finds all solutions across the cluster. Query results compacted by picking one representative from the cluster. Option disable same as equals true. Disable same as equals false equals expand results over equivalent URIs.